The computer science department established an AI track in the master's program in 1981, and I was in the first entering class in 81, so class in 1983, then went on to attend some of these computer forum meetings as a graduate student in the Knowledge Systems Lab doing my PhD. Then I went off to the East Coast, trained in radiology, stayed there for 25 years, so I'm very happy to be back at Stanford and especially happy to be back here with you today. I thought I'd tell you about some of the activities related to how AI is being used in the School of Medicine. It's very exciting. Here are my disclosures, which the school wants me to tell you about. I also just want to thank all of the many collaborators that I'll mention as a part of the talk. I know this is a non-medical audience, so I thought I would start with, what is radiology? So we have CT, MRI, ultrasound, X-ray, all different ways of obtaining images. We create these beautiful pictures of the human body, and then someone like me sits at a high-resolution computer workstation and interprets these images. And actually, unfortunately today, we use automated speech recognition, but we dictate a narrative report. Narrative that describes what's on those images, and that's what's used for clinical care. I want to start with a case. So this is a 83-year-old woman who had a chest X-ray. She does occasionally, has some trouble with congestive heart failure. And this is really not very fair in a brightly lit room like this, but she came back about 18 months later and had this large mass. And if you look back at the prior image, you'll see that there is this small mass. It's partially overlying a rib. There's some vessels in that area. I think a radiologist on a good day would have seen this, but this particular radiologist didn't. And the rate of errors in diagnostic medicine, diagnostic errors, is about 3 or 4%, and that's certainly true in radiology. I read 100 chest X-rays or so yesterday. I worry about that, and certainly we all feel like we would be happy to have some help from computer algorithms. What got everyone in medicine excited about this, particularly in the medical imaging disciplines, this is work like this. This is Fei-Fei Li's lab doing this automated captioning of images, a bottle of water, cup of coffee, plate of fruit. That's really what we do. We look at images, we describe the various aspects of those medical images and create either a narrative or a set of structured reports. So how are we responding to that in the School of Medicine? One of my other hats, as was mentioned, is I'm the physician responsible for the information technology that runs our radiology practice. So we have about 0.5 petabyte of imaging data. That's about 5.5 million studies. It's about 1 billion individual images if you count them up. And we are in the process of migrating a copy of that to the cloud where it can be merged with these other forms of data, the electronic health record data, so your standard medical record data, omics, genomics, proteomics, biobank, tissue bank information. So those are de-identified, but in a way that they can be linked and used for research. We have that as part of a data common. Some of that is in the cloud, some of that is on-premise, and then we have a set of applications that can be used on top of that to help our researchers perform the kinds of work that I'll tell you about. We also are, we've formed a center for AI and medical imaging. We have affiliated about more than 40 faculty across 8 departments in 3 schools, primarily the School of Engineering and School of Medicine, with active collaborations, particularly with the 3 computer science labs you see there, Andrew Ng, Fei-Fei Li, and Chris Ray. I'll tell you about each of those collaborations in a minute. The kinds of research questions that we are addressing really start with what most healthcare organizations have, and that is very large image databases and very large corresponding reports. So for our 5.5 million images, we have 5.5 million narrative reports that were created by the radiologist at the time that that image was obtained for the clinical care of that patient. That turns out to be a ripe source of labeling. So we spend a lot of our time, this is really one of the key bottlenecks, is creating large enough sets of labeled data that can be fed into machine learning algorithms. So we spend a lot of time with natural language processing algorithms and information extraction from those narrative reports. As you might imagine, much of the work in computer vision was initially done with databases like ImageNet, large numbers of photographs, 256 by 256 color photographs with a dominant object. We deal with images that are much higher resolution, higher dimension, and so we think a lot about what kinds of algorithms we need that can create efficient enough machine learning for these complex images. And then explanation methods. So like finance and some other disciplines, in healthcare, we've got an expert who has their own opinion, and they are going to be paired with or partnered with a decision support system that's going to provide them some advice. And so we think a lot about how these systems can explain how they came to their conclusions so that the person working with that decision support system can evaluate the advice. And then we'll talk a little bit about the weaknesses of generalizability, the brittleness of some of these models. So we are concerned about clinical evaluation. So when we build one of these, the next thing we think about is how can we put it into one of our radiology reading rooms and evaluate how it actually performs in clinical practice? How does it affect the accuracy of that radiologist? So a bit about labels. We are fortunate here at Stanford. We had a radiologist about 10 years ago who decided that that we should start collecting discrete information about our results. So at the bottom of each report, for a period of about 10 years, we saved a discrete code that describes whether that whether those images are normal, whether they're abnormal, or whether they're critically abnormal. And those human labels have turned out to be very valuable for us. So when we have those human labels, and we intend to continue to expand programs like that where we can create discrete information as part of the clinical care process, we can then develop these large, highly accurately labeled training sets. We also use a number of techniques on the retrospective reports that don't have these labels and to extract more finely grained information. So this is a technology that we built when I was at the University of Pennsylvania, just a simple reverse index search of these large databases with some filtering technology that allows us to very quickly generate reasonably accurate cases of positive examples of a given disease or disease state. We also have used fairly standard machine learning techniques, conditional Markov models, conditional random fields to do information extraction from the radiology report. So here blue is anatomy, green is an observation, orange is uncertainty, and we can extract those. And we're working on extracting the relations between those, as I'll show you in a moment. Chris Ray's lab has developed something called Snorkel open source, which is a very nice rule-based labeling technique, so we can use that on our radiology reports. Show me all the reports that have, the word brain within 5 words of the word hemorrhage and all the different permutations, and we can generate from that some fairly accurate weak labels of our images for machine learning. And then we've, of course, applied some of the same neural network techniques, CNNs, LSTMs, to the text itself in order to do some fairly accurate information extraction. We are fairly early on in our quest here, just a couple of years old. One of the projects that's our newest is we're starting to work with Fei on what she calls visual genome. So this is the ability to automatically learn a scene graph, not just labels, but a scene graph from an image where you have bounding boxes of various objects and then a semantic network that connects them behind the scenes. We think that radiology is actually very amenable to this kind of a scene graph because we're working typically static in time. So we're talking about today, right now, what the images show. We know that typically we're going to be describing anatomy and we're going to be describing disease and how the disease affects the anatomy. So it's a relatively limited information model behind it that we can use to create some of these scene graphs. So we're working through the labeling process on this right now. I want to show you some of the models that are probably closest to clinical testing. So this is a model for bone age. So the clinical problem here is children who have developmental delay we often need to decide what is their approximate physiologic age and compare that to their chronologic age. So we take an x-ray of the hand, we look at the bone development in the hand, and that can give us an estimate of their physiologic age. The current state of the art for this is a book. And the reference data in that book, by the way, the book happens to be the largest, the most profitable book ever published by Stanford University Press. I just learned this the other day, interesting fact. But it's, you know, it's one of these golden oldies, every radiologist needs a copy. And the book has reference data from 300 Caucasian children who grew up in Cleveland in the 1950s. And so we look through the book, we turn the page, we say, 7.5, yeah, that looks about the same. This child must be about 7.5 years old. So we thought this was a ripe application for machine learning. And you can see here, the reviewers here are the humans, and the model here is the algorithm. And this is a mean absolute difference, so low numbers are better. And you can see the model's performing maybe slightly better than 2 of the humans and about the same as 2 others. So we're getting human-level performance out of this model. These are the kinds of Saline Sea Maps that you see, just that would give the radiologist comfort that the model is looking at the right places. We're looking at the growth plates in the fingers and in the wrist. That's exactly where the model should be looking. So the interesting thing about this now is that we can very rapidly create these models for different demographic groups. So now we don't have to worry about, we don't have to take data from the book. We can use it for whatever the local demographics are and get much more accurate answers for specific individuals, so a kind of precision medicine approach. Another example, that was the work of David Larson, by the way. This is the work of Matt Lundgren, collaborating with Pranav and Andrew Ng's lab. The NIH, National Institutes of Health here in the US, released over 100,000 chest x-rays that were labeled, weekly labeled, for 14 different conditions. And these numbers are area under the ROC curve. So we had really quite good performance that exceeded 2 of the other models that had been built in this area. And here is just a comparison. Note the scale here, but this is a comparison of the area under the ROC curve for the various conditions. You can see that the model was better than the humans in 1. The humans were better than the model in 3, and there was no difference in the other conditions. So again, we're getting close to human-level performance, or at least an algorithm that would help a human radiologist interpret a chest radiograph. This is the work of Greg Zaharchuk's lab. He's a neuroradiologist. And this sequence is called arterial spin labeling. So looking here at the brain, on the left we have a high signal-to-noise image, and on the right a low signal-to-noise. So the one on the left would have taken much less time to create. We can then use information from some of the other sequences we obtain anyway that are higher resolution, provide better anatomic spatial resolution, and create a synthetic image that's equivalent in quality to the longer image. Greg has also done work on PET scanning. So this is where you get injected with a radioactive substance, and then a machine tomographically counts the emissions from the body and figures out where the radio tracer went, and that helps us find disease. He's shown that we can dramatically reduce the dose, so we can use a very low dose of radiation to get the same amount of information. So this is an extremely active area right now, typically using UNETs as a method to enhance image reconstruction for MR and a variety of other CT and nuclear medicine. So where is this being applied in medical imaging today? So I just showed you efficient image creation, quality control. So we often have patients who come and they lie on the scanner. They may be moving or breathing, and the images are not of good quality. That doesn't get detected until a radiologist looks at it maybe an hour or 2 later. Now the patient is at home, the intravenous contrast has been excreted, and the patient has to be brought back. It causes a lot of problems for a variety of reasons. So if we could embed in the scanner device algorithms that would detect those suboptimal images and remind the technologist who's operating that device to repeat that image, that would be very valuable to us. Workflow optimization. So as I said, I'm a chest radiologist. We get 50 chest x-rays from the ICUs, intensive care units in our hospital every morning. The reason those are done is to screen for serious abnormalities, and maybe only a few of those every morning will have something serious. And so an algorithm, that's one of the things that algorithm I just showed you could do, is to detect those and to pop that to the top of my list so I look at those right away as opposed to maybe at the bottom of the list later in the morning. Very valuable, can save time, patients in the ICU, and get earlier antibiotics for pneumonia, that sort of thing. Intelligent user interfaces. So right now, if I'm a radiologist and I click on something, I want to measure, let's say, a tumor in the liver, the software has no idea that I'm looking at the liver, has no idea that I'm measuring a tumor, and just to know, to learn, to segment that, to know that I'm in the liver, to know that I'm measuring a tumor, to compare it to the prior exam, to graph it out over time, all those kinds of things. Fairly simple things, but would be very valuable to us in terms of our workflow clinically. Computer-aided detection would help us with the task I showed you at the beginning, that chest x-ray, and we've used that using good old-fashioned AI technology in breast imaging for some time now. Computer-aided classification, so this is where we have a radiologist who's maybe out of their comfort zone. We train across a whole broad range of imaging types and body parts, but tend to specialize in one or another. So if I'm a chest radiologist, I see something in the bones that may not be particularly familiar to me. So it would be great to have put a circle around that and have an algorithm help me with what are the most likely diagnostic possibilities for that lesion. And then automatic report drafting. You can imagine if for a given image type you can build detectors and classifiers for the most common abnormalities in that image type and pair that with some standard text generation, you could actually draft the report that would be a part of that patient's chart. That's, I have humans, we have radiology trainees, residents who do that for us, and it makes us much faster as faculty, but 80% of the world is out in private practice and they don't have that benefit. So there's a real opportunity there. Okay, challenges. Data availability, as we've said, particularly labeled data. Every hospital has a lot of images, but getting that labeled properly, high-quality labels for machine learning, that's a challenge. Complexity, I'll show you that in a minute. Transparency, how these models explain themselves, and generalizability, the need for clinical validation, and then regulatory and clinical integration. So I'm going to talk about a few of these. So this just gives you a sense of a variety of images that we have in our really all radiology departments have. And pathology is yet another image type that would be more complex, and ophthalmology, endoscopy, different as well. So you can see everything from 4K to 4K with a 16-bit depth, and then we've got maybe lower resolution. Some of them have video. Most are black and white, but some color. So a variety of different data types that we need to work with. We also, as I said, unlike photographs, typically we don't have one dominant object. So this happens to be on the right is a slice of a CT. The arrow is a tumor. The arrowhead is a loop of bowel filled with fluid that happens to be sliced crosswise and looks very much the same. And you can see elsewhere in this image, this is a vein, this is an artery, and there's a whole bunch of other things going on in these images. So finding the focus, particularly if the only labels we have is whether it's normal or abnormal, that poses challenges. We need to build attention models and other things that help us build effective models in those settings. You've probably seen this, but this concerns us a great deal when you talk about the health of patients. These models are brittle, so here's someone has found stickers that can be placed on stop signs so they're not recognized as stop signs. Clearly a problem with self-driving cars, one of the other applications of this technology, but we worry about this sort of brittleness in the models that we build as well. Here Google has designed this medallion that if you put it on any photograph of an object, it automatically thinks everything is a toaster. So those kinds of things can be a problem. Okay, I want to just close with some maybe social implications. When radiologists and other diagnostic imaging professionals got wind of the capabilities of some of these systems, there was a fair amount of concern and anxiety about whether they might be replaced. And my experience going back actually to the 80s is that any kind of decision support system like this in medicine can be as good as a specialist, but typically the system and the human together are better than either one alone. But this is Jeff Hinton, one of the pioneers in this field, as you know, who was asked about radiology. He said, let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't looked down, so doesn't realize there's no ground underneath. We should stop training radiologists now. So this is a serious concern, and I was receiving calls from medical students saying, gee, I like radiology, but should I really go into it? Is there going to be a career in it for me? So this was a concern across the field. Here's Harvard Business Review: robots will replace doctors, lawyers, and other professionals. Here's Andrew Ng. I'm more likely to be replaced than my administrative assistant. I think he's maybe changed his tune on that a little bit. But here's New England Journal: machine learning will displace much of the work of radiologists and anatomical pathologists. Actually, now radiologists are embracing this technology and recognizing that it's something that's going to help them do a better job and is going to, in fact, invigorate the profession. When I speak to radiologists, I talk about autopilot. So this is the cockpit of an Airbus A380, and I always ask for hands. Who would fly in a passenger airplane with no human pilot? And I think the analogy there is very similar to ours in medicine, where we have a high stakes, we've got a primarily visual activity, and there's a need to take a lot of data and integrate it and display it to an expert. And so I think what radiologists are going to get from the work that we see here is better autopilots, in a sense. So we're all very glad that there's a human being in the pilot who knows when to turn on the autopilot, when to turn off the autopilot, and fly the plane. And we have the same need with respect to our technology. So this is a photograph. The guy standing here is named William Morton, who popularized the use of X-rays. This is from 1896. Popularized the use of X-rays in the United States. And sitting here to his left is Edwin Hammer, who is an engineer. And I think this is a metaphor, again, for radiology, which has been bringing high technology in service of patients for over a century. When MRI first came out, people said, well, the pictures are just so clear, you're not going to need a radiologist to interpret it. But it turns out there are physics associated with MRI and artifacts, and so we needed to learn how those systems work, what their failings are, and how they can integrate into our current clinic. And I think the same will be true with these AI systems, that radiologists will have to be trained about them. So I think radiologists are here to stay. Computer scientists are our friends. We're going to continue working in concert with our collaborators here on these exciting new tools. We're really excited about our relationships with computer science and our collaborations. We think there'll continue to be a push-pull between medical problems and computational methods to develop new ways to interpret these complex medical images. I'll stop there. Thank you. Happy to take questions.
Hello. Hi. This is Fan. I'm from Oppo. So you mentioned that one of the biggest challenges of the data preparation, and we have a similar problem before for the non-nodule detection. So one of the problems is on like the common sense that everybody thinks this is a chair, but in this case, the data requires very well-trained radiologists, right? But even between the radiologists, right? One radiologist from one hospital compared to other radiologists from other people, they have a different view towards one single images. Yes. So that's a very big problem of the data consistency of these annotations. So what's your thoughts on that?
Great question. Yeah, so we think about that a lot, and it's so true. There is a great deal of variability, even among expert radiologists, and we saw that in that bone age study where we had 4 radiologists. So we think about that in a couple of ways. First of all, we found with the chest X-ray work, many people analyzed the labels that the NIH had put on that chest radiograph work, the 100,000 chest radiographs. They were not very good, to say the least. And yet we were able to get human-level performance. So that's something that we find over and over again, that we actually don't need perfect labels to create a great model. Having said that, we do need to validate. We need an accurate sense of how accurate the model is. And we can't use noisy data to do that. So what we have typically done is, for the chest X-ray work, we ourselves had a group of radiologists, expert radiologists, chest radiologists from here at Stanford, manually annotate and label, I think it was about 430 cases for those 14 conditions, and use that as our evaluation set so that we can get an accurate sense of how the model truly is performing. And there are some rather complex statistical methods to manage the inter-observer variability that you see. So you're comparing essentially how does the computer compare to the human versus how does the human compare to the human. And so through that, you can at least get performance that is as good as the best radiologist. But so that's one way to answer the question. That there are really two classes of problems. So one is what I just described, so where you have something like a nodule that is pretty clear the radiologist is going to say it's there, it's not there, it's very clear on the image whether it's there, and we know what the truth is just from the image. But then let's say we have the problem of whether that image is, whether that mass or that nodule is cancerous or not. That's something that the radiologist cannot know at the time. And so for that, we go back to the electronic record. That's where that system in the cloud is very helpful to us. And Nigam Shah, one of the biomedical informatics researchers in the School of Medicine, does a kind of digital phenotype. So he can use these same machine learning techniques and apply them to the information in the medical record and say, does this patient have cancer and do they not, and when were they diagnosed? And then we can use that as our ground truth. So we find ways to work around that inter-observer variability, and we've been able to create so far, using these various data sets, some models that perform at the level of humans nevertheless. Yes?
So great talk, by the way. So I have a quick question. So you talk about data accessibility, especially labeling is one problem, but medical data accessibility from the actual researchers is also a problem. So can you talk more about how this can be shared among different researchers and potentially even be public,
yes.
Based on kind of creating Dr. Fei Li's
yes.
ImageNet.
Right.
In the medical
yes, and we've branded ours with Fei-Fei's permission. Ours is called Medical ImageNet, so we're leveraging that brand. Yes, it's a difficult problem. So we have HIPAA, which is this law that is about the privacy and shareability of imaging data, and that does restrict us to some extent. A couple things that we're doing. So we can share. The School of Medicine can share its imaging data and labels with other laboratories and other companies through partnerships that are mission related to Stanford, right? So if we have a collaboration with a company, which we often do, we can share data with them for those projects. We can share it with other laboratories. We also have, we made that bone age data set public for a challenge. That's a little more difficult because of the need to de-identify the data for privacy purposes. So if you actually expose publicly any data that can be identified back to a patient, that's a breach of that HIPAA law, and there are all kinds of provisions that kick in and notifications and other things, so that's something we avoid. So we actually have a manual process of fairly unskilled labor that comes through and looks at each image to check, after we do the automated de-identification, to check that it has been de-identified. And then, of course, we're using that as a data set to build a machine learning model so that we can further improve our automated methods. But ultimately, we have to be very careful when we make data public for that reason. The other thing we're doing in this regard is, and this is Daniel Rubin in our School of Medicine, he's in radiology as well. He's been developing methods so that you don't need to move the data. So let's say you have a rare condition where we don't have enough instances of it here at Stanford, so we want to collaborate with 5 other institutions. So we now move the model, essentially, move the parameters rather than move the data, and train it a little bit in each place and rotate around. So we're looking at Daniel's looking at what are the best methods to optimize that distributed training of a model.
Sir, I have a quick question.
Yes.
It's a very wonderful talk, and Can you see me?
Yeah, I got
Sorry.
you.
Okay, I'm from Osama Khatib's lab. We're very interested about the medical image. For the MRI and the CT are pretty standard image processing or acquisition system. But for ultrasound, it's heavily dependent on the user manipulability and the dexterity. How can you improve the image quality? I really like the idea you see the AI can help with the image quality or quality control.
Yeah.
Do you have any idea we can improve that?
Yeah.
Thank you.
Sure. This is not out of our center. There's actually a startup that's spun out of Stanford that's doing this work. So just from background, what he's describing is that for ultrasound, you've got this essentially microphone, and you've got to orient it in just the right way to get the right projection so that you can interpret that image appropriately. And so it's operator dependence is what we call that. And what this company has done, and this is for a hip ultrasound in a child, is you can have a relatively unskilled person sweep the transducer multiple times over the area and then have build a learning algorithm that can view the video of that and freeze it or reconstruct the appropriate projection. And that's really important because ultrasound, being fairly portable, non-radiation, is widely used in the developing world, and the application of this to the developing world is actually huge. And so there you tend to have less, you can then more widely distribute that technology to less skilled operators using methods like that.
Sorry, could you repeat the name of the technology?
It's called viz.ai, viz.ai. There are about literally 50 companies in this area of radiology and AI right now. It's startup heaven.
Thank you, Curtis.
Thank you.